Hi there! We're going to describe the evolution of population sizes. This evolution will be given by a discrete dynamical system. We will see how matrices will be very useful in this description. Suppose we start today with a colony of 100 young mice. We will count the number of mice once a year, every year on the same day. This is exactly what makes this model discrete instead of continuous. We do not consider the population size at any time between today and 1 year later. How many mice will there be in exactly 1 year? Well, the mice will obviously get older, and some of them will die. But they will also produce offspring. These fertility and survival rates will depend on the age of the animal. Let's give some numbers. We will call a mouse young if it is less than 1 year old. Here you see 10 young mice. They all have a survival chance of 30%. So, out of every 10 mice we see at a certain time, on average 3 will survive until next year. Obviously by then they will be at least 1 year old, so we will then count them as adults. The young mice produce offspring. Let us say that on average every young animal that is counted today will have produced 1 offspring by next year. This means that by next year our starting population of 100 young mice will have evolved into a population of 30 adult mice and 100 young ones. What about the adult mice? Here you see 10 of them. They are more likely to die. They only have a 10% survival chance. However, they are more fertile than the young animals. On average, they each have 2 offspring by the next year. Let us put this into equations. We will denote the number of young mice and adult mice at time k by yk and ak respectively. Since today at time k equals 0 we have 100 young animals and no adults, we can say that y0 is 100 and a0 is 0. Now, if we know how many young and adult mice there are at time k, can we predict their numbers 1 year later, so at time k plus 1? We sure can. First, how many young mice are there? We define young as less than 1 year old, so this is the new offspring. The yk young ones that were alive at time k each produce 1 offspring, so this gives 1 times yk in total. The ak adults that were alive at time k each produce 2 offspring, so this gives 2 times ak in total. Together we have yk plus 1 equals yk plus 2ak. How many adults are there at time k plus 1? Well, out of the yk young mice at time k, 30% survive. So this gives us 0.3 times yk adults. And 10% of the ak adults survive and obviously stay adults, so we get this equation for ak plus 1. These are 2 linear equations, so we can write them in matrix notation. We will denote the square matrix L in honor of the biologist Patrick Leslie, who developed this model that was named after him. By giving the population vector at time k the name xk, we can write our model in a very concise way. These are all different ways of formulating the same discrete, dynamical system. Let us now use our formulas to find the population vector at time k equals 1. This is the Leslie matrix multiplied by the population vector at time k equals 0. We again find that after 1 year we have 100 young mice and 30 adults. For the situation at time k equals 2, we get the Leslie matrix times the population vector at time k equals 1, which shows that after 2 years we have 160 young mice and 33 adults. Here you see the population sizes up to year 8. You recognize the numbers we obtained for years 0, 1 and 2. Don't worry too much about the non-integer numbers later on, this is just a model. But we do get a lot of mice after a while. So, if we are willing to perform a lot of computations, we can find the population vector at any time k. It is interesting to notice, though, that we do not need to go step by step. Suppose we want to know the population vector after 8 years. As we now know, this vector is a product of the Leslie matrix and the population vector at time k equals 7. But this population vector at k equals 7 can also be rewritten as the product of the Leslie matrix and the population vector at time k equals 6, and so on. We notice that we now need the 8th power of a matrix. That sounds like a lot of work. However, in class you will see a method to calculate this pretty quickly. Finally, as a little teaser, let's take a better look at the numbers we just obtained. Here you see the growth factor. In the first year, we went from 100 animals to 130 animals, a growth factor of 1.3. The next year, we went from 130 animals to 193, a growth factor of 1.485, and so on. These values seem to converge. And this is not all. As you can see here, the percentage of young animals in the population tends to a constant as well. The values to which the growth factor and the fraction of young animals converge are actually no strangers to you. Perhaps you can already find out how you could find them. For more on this, see you in class!